Hi everyone, this is Madhav and I'm making a visual introduction to this topic that people like to call solids of revolution. I never really liked this name, I never really liked the textbooks, they were always confusing because I couldn't see what was going on. So I'm gonna hope to show you what is going on visually using some CAD modeling and Desmos today. So in Desmos, you can see I have a equation here. If you're struggling to understand this, maybe not the tutorial for you. I'd say you probably want to know grade 12 math if you're looking into solids of revolution. That said, I have this function in red and we're going to be focusing on this area. What solids of revolution are is taking this shaded area you see, revolving it, creating a 3D shape out of it, which already, sounds a little bit mind-blowing in this 2D graph. And then we're going to do some fun stuff with it, like compute the volume of such a shape. Because this is a 3D thing though, I'm going to switch over from Desmos to a CAD modeling software called Fusion 360, where I'm going to create this curve, f of x equals 1/2 times 2 to the x, and then we're gonna get to answering that question. How do we create a 3D shape out of this thing? So here in Fusion 360, I'm going to first of all recreate that curve. So to do that, I'm going to select this axis to work with, which is just this plane right here, and I'm going to create a spline, which is a fancy word for a curve, so that we can work easily. I'm going to change my units to centimeters, and now you can see, at least I hope you can see as I zoom in here, we have 1, 2, 2.5, 3, so on. So we're working with centimeters now. Because of that, it's going to let me quite easily replicate the curve I have here. So I know I should start with a point at 0.5. So 0 centimeters this way, 0.5 centimeter this way. Then I move to 1, over here somewhere. And then 2, and 3, 4, and 4, 8. So I'm just going to go and draw out those points. So we have around here, that's 1.5 centimeters roughly. Then we go to 1, 2, 2, 3, 4, and then 4, 5, 6, 7, 8. There's our curve. So I'm going to click here. You can see we have a curve that looks like this curve over here. Axes are a little bit bizarre, but roughly looks like it. I'm also gonna draw these straight lines around the edges so that we create a closed shape to work with. So to do that, I'm just gonna take this, draw down, move over here, oops, take this, move over here, and then close the shape. There we are. And you can see now we have our base shape, this shape which looks like this shaded area. Cool. So now that we have this, I'm gonna answer the question, how do we create a 3D shape out of this 2D curve? How does that mess work? What I'm gonna do in order to show you is I'm going to first of all hide this for a little bit, and I'm going to revolve it. We have the name solids of revolution for a reason. So I'm going to take this shape that I had and revolve it around this x-axis. So I'm just going to select it for now, and then you'll see what's going on. So let me show that shape again. You see this shape, it's going to go revolve around this x-axis. Let me choose it. It's gonna autocomplete, but don't worry, I'm gonna show you a little bit more step by step what is going on. So I'm gonna take this slider over here and let's go all the way back to the beginning. There we are. So as I move towards the right, take a look at what's happening. It's basically pulling the shape along a circular path, i.e. it's revolving the shape. So, I'm pulling. In each of these moments, you can see the shape that I get, the face, it's basically the same as the original shape, right? So the shape is just being, rotated around this path. To show you from another angle so that it's, it stays visual, you can see I'm taking the shape and I'm revolving it, revolving it 360 degrees, revolving it clockwise, anti-clockwise. I hope this is showing you the first thing which, always confused me. What does it mean to get a solid or revolution? Like, what are you doing? You're taking a shape and then you're revolving it around some axis. You see? So with this revolution done, I'm just gonna, make it a complete revolution, so 360 degrees, and I'm gonna press OK. So now I have my shape. So what just happened? What just happened is we just took this curve, f of x is equal to 1/2 times 2 raised to the x, this weird equation. We selected the area between x is equal to 0 and x is equal to 4, and this curve and the x-axis. So this red area over here, we took it and we revolved it around the x-axis. When we did that, we ended up with this shape, which looks a little bit like the base of a stand that a lamp is, being held up on. So that's her shape. Hopefully that's visual enough to follow along, right? It looks a little bit weird with the texture, but whatever. So we have our shape now, our 3D solid that we got by revolution. Hence we have a solid of revolution. If I go to Fusion 360 and I ask it to tell me a little bit about this shape, so I'm going to click on properties here, you can see it's telling me what the volume of the shape is. It's precisely 144 point whatever cubic centimeters. The key question, and one of the most important concepts in solids of revolution, is how do we know that? How do we know what the volume of this random shape is, right? Like in high school they tell you, okay, the volume of a cube, you just get it by multiplying the side length by itself 3 times. For a rectangular prism, take the base, multiply it by the height, multiply it by the length, and you get the volume. Well, for this weird thing, how do we get the volume out of here? That's really weird, right? Well, the key thing comes from this face, the key hint. If you take a look at this face of the shape here, you can see it's a circle. And we know how to compute the area of a circle, and what would be very convenient is if we could take the area of a circle multiplied by a height and get the area of a cylinder. That would be very convenient, we know how to compute the area of the volume of a cylinder, right? It's just the circular base times the height. Okay, but the key issue is that this isn't a cylinder, as you can see. It like shrinks in on this end and then it expands on this end. How do we deal with this? Well, what if we could, cut this shape up into many tiny discs, very, very thin discs that resemble very flat, thin cylinders. I'll show you one very crude example of this. So let's say I zoom in on this side. You can see over here I have, the circular face, which kind of looks like the start of a cylinder. The only issue is that it starts to like expand on the other side. What if I took a plane here, so I take it from here, move it, let's say 0.25 centimeters, and then I chop off this end. I'm gonna chop this end off. So I'm gonna take this, split the body with this plane. What I'm just saying is I chopped off this end. So now I can take this end. You see I have a new shape. I'm gonna take this end and I'm gonna move it. So I'm gonna translate it so that it's a little bit further away from the shape. Alright. So now I have this tiny end that I chopped off. Could I find the area of this part? Let's just not even worry about the rest. Could we break down the problem? Could we make it a little bit simpler? Well, if we just take a look at this part, then it's kind of easy, right? This is close to a cylinder. You know, it's a little bit different from a cylinder, but it's pretty close. And to show you that visually, let me make a quick copy of this so that you can see how it doesn't take much, imagination to get this to be a cylinder. So I'm just going to take this, make a copy over here, right? And I'm just going to make this a cylindrical shape, and you'll see that the difference between the two shapes is not very large. To do this, technically I'm doing something called extrusion. Don't worry about it. This is a math video, not a CAD video. There we are. So you can see these two shapes are pretty similar, right? There's just like this little angle that's missing from the top and bottom, but that's not too big of a difference. So what we could do is we can approximate the volume of this cylinder, which is a simple shape to calculate the volume of, because it's just, this length of this line times the area of this circle. We can approximate that to be the same as the volume of this odd looking shape, which is technically called a frustum of a cone, whatever. It's approximately a cylinder. This gets more and more and more true the more thinly we slice these sections of the final shape, the big shape that we had. The more thinly we slice this up, the more finely we chop it, the more the chopped sections resemble cylinders that we can easily compute the volume of. And so we will compute the volume of each little cylinder and then add them together, and that will get us the total volume. Now to show this to you, because it takes a little bit of time, I went and I chopped up the shape into a lot more tiny sections. You can see all of these lines, they have, I chopped the shape up, and to give you even more intuition, you see I'm splitting the shape up here into different chopped sections, right? So I took the whole shape, added in many slices, I moved them apart, and what I'm saying to you is that each of these slices, they're approximately a cylinder. It's just like the end angle here, that's a little bit different. So we can take all of these little almost cylinders, right? We take all the almost cylinders and we can compute the volume of each of these and then add up all the volumes we get, and that will give us the volume of the larger weird shape. So this is the key insight of solids of revolutions. What we do to get them is first we start off with an equation. We select a part of the equation, like this part bounded in red. We will take that part and we will create a sketch out of it, like so, revolve it around an axis like I showed you, and that will give us, it will give us a full-on solid 3D shape that looks a little bit weird. We can take the 3D shape and slice it up, either in the horizontal direction, in the vertical direction, doesn't matter. Whatever gets us simple shapes to work with, like just cylinders, right? So we'll slice it up into extremely thin and tiny pieces, and it will let us split apart the shape into many smaller shapes. When we have the smaller shapes that are, approximately a cylinder or any other simple shape, then we can estimate the volume of the big shape with all of the small shapes volumes added together. So this is our visual introduction to solids of revolution. As you might expect, if you've taken a math course, immediately the shaded thing, it reminds you of something called an integral. So you can expect that there's some complexity, some math that we will use very soon to compute the volumes of each of these tiny sections. But just keep in mind this visual intuition as you go, learn about those math videos in textbooks or whatever, because I find that you can get very easily lost in the formulas they give you without remembering, like, hey, this is what we're doing. We're chopping up a complicated shape into simpler shapes, many simpler shapes that make it easier for us to solve the problem. So if you're interested in more details, see the links for the technical resources in the description.